Thank you very much. So, type systems. I have to start with a disclaimer whenever programmers talk about type systems, right? Because normally when you get into a conversation about type systems, especially on the internet, it's like, right? You got someone over here saying, static type systems are better because they're more correct and I can write correct programs. And someone's over here saying, dynamically typed systems are better because I can write what I'm thinking and I can just express myself. And it's horrible. I mean, we've been making that argument for decades, and I think all the light has drained out of it, and it's just heat. So I want to reassure you that this is not a talk about correctness or type systems being better than untyped systems or anything like that. So if you take away the whole correctness argument, in fact, I want as far as possible to even take away the compile and run it argument. What is left? I would like to tell you a story about types. So I started, I'm forgetting the year now, but a while back, let's say. Let's not give away my age. A while back, I was working in Clojure, and I got into a company that used Haskell, and I started getting interested and started learning Haskell. And something I found back then was that the documentation was terrible. You may have found this yourself. And it has improved, but one thing I heard, which is absolute nonsense and an absolute lie, was, oh, we don't need documentation, we have types. I mean, bullshit, right? It was bullshit, and it's complete nonsense. You will never get rid of the need for prose and explaining yourself clearly. But I didn't appreciate at the time that while types aren't documentation, they do overlap. The purposes of types do overlap with the purposes of documentation. And where they overlap, types have some nice properties, like your developers are guaranteed to update them. They are guaranteed to be accurate. And what I found as I learned more Haskell is that a good type signature can tell you far more about the code than you ever thought. So I want to try and introduce this idea to you. We're going to talk about how types can help you, not about correctness, but how they can help you communicate with the rest of your team. Communicating your ideas about how systems should work to other programmers. They can help you not only now, but in the future. Because another problem with documentation is it ages, and it tends to age like milk rather than wine. Whereas types, because we are sort of guaranteed that they're up to date and accurate, that can be messages that we send to us in the future and our teammates in the future. And I always think, as a slight aside, every software project you write is on a team. Even if it's just you using your laptop, you're still on a team with you in the future, and that bozo that wrote this code 6 months ago, right? And a good type signature, as I hope we will see, will help you analyze code from different perspectives, to think about code in different ways, because it's like a high-level executive summary of what the code's actually doing, rather than what it's supposed to do. So, what do I think a good type system is? I think there are 2, maybe 3. We're going to talk about 3. I'm going to try and convince you there are 3 things that a type system should do for you. And you could argue which of those is the most important, but I'm going to start with describing things. How do we describe data? I think data is the fundamental unit of building a system. We start with data and we build up. So, you know, we've been doing this for decades now. We must have good ways of describing data, mustn't we? We should. We really should. How do we describe data? We don't do it like this. We tried. This is SOAP. Anyone remember SOAP? Anyone scarred and twitching? Wow, that side of the room is the scarred side of the room. You guys, you're surviving much better. For a while, we were told this would be the future of describing data. It's horrible, and I think the reason it's horrible is it's anti-human. It's inhuman. It's not really designed for a human being to read or to write. It's accurate. I like the fact that it's accurate, but humans aren't supposed to touch this stuff. You're supposed to get in a Microsoft consultant to do it for you, I think. Okay, so if not like that, and I pick on SOAP because it was a particularly interesting time when we started to try and talk between systems in the history of the internet. If that lost, what won? And the answer is definitely JSON won. JSON won this argument. Why? Because it's machine readable, machine writable, human readable, human writable. And that's a fundamentally great property. The problem with JSON is it doesn't describe data. It gives you a specific instance. Look at that. There's an order. Looks straightforward enough, but payment method Visa. Can it be MasterCard? Can it be Bitcoin, cash, IOU? Is it sometimes null? Dog? Could be dog. Could be cat. Could be lolcats as a meme coin. I mean, who knows? This is not a data description. This is a data example. This is data. It's not a way of describing data. Have we got any other tricks for describing data in our industry? I'm really picking on Java in this talk at points. Have a look at this one. For a while, we were told this is the future of describing data, but please don't describe data. You must not describe data. If you describe data without describing the processes attached to it, the methods, then you are a bad programmer and will be sent back to the YOW gulags for retraining. It has improved. I'm picking on Java. It's improved with records. And why has it improved? Because it started to think about just describing data. And of all the ways I've found of describing data, the best one I've found has the worst marketing name. So let me hit you with it, see who I lose on this. Algebraic data types. Trips off the tongue, doesn't it? What the frick is an algebraic data type? Let me see if I can mostly explain why it's good, and maybe as a bonus, we'll explain why they're algebraic, right? So, there are two big components to algebraic data types. And the first one you'll see in every language I can think of, and that's called a product type. Take some basic types, merge them together to make a larger, more complex type, right? So these are called structs, these are called records, objects, if you take away the methods, like JSON objects, Lua calls them tables, you'll find them all over computing, because it's a fundamental thing we need to do. Mush types together, mush being the academic term. As a slight aside, why are they called product types? Because you count up the number of possible values. The number of possible values of order ID multiplied by the number of possible values of value, multiplied by the number of possible values of payment method, gives you the number of possible orders in the universe. So it's a product, you multiply. And one of the reasons I mention that is you may think to yourself, okay, if there's a multiplication, if there's a kind of and of types, is there an or? And many languages, not all of them, have an or, which is a sum type or an enum, right? I've got clothing size, small, medium, large, extra large. If you've ever done one of those books like Teach Yourself Java in 24 hours, it probably used clubs, hearts, spades, diamonds. That's the default example. Oring types together. The number of possible values is 1, 2, 3, 4. Right? That's why it's called a sum type. You just add. So, at the moment, we're at every language has the first one. Many languages have the second one. But what makes algebraic data types really, really good is the ability to combine them freely, to mix and match. So have a look at this data. Have a look at this data description. Order response. What kinds of order response are there in our system? Purchase successful, payment failed, network error. Now, I just look at the description of the data, and I feel I can learn quite a lot about how this system works. For example, I know that orders may succeed or fail, simple enough, but I know that we make a distinction between different kinds of failure. I look at network error and I think, oh, status code, int, I bet we are talking about placing orders over the internet, right? Probably a 500 or a 404 in there. I can make some educated guesses. But we also have payment failed, which instantly makes me think, I bet there's a different UI widget for that kind of failure than the generic network failed. The more I look at this data description, the more I think I can see what the eventual actual system will look like. This little nugget of information almost seems holographic in that it projects out into the entire way the system's going to work. Let me give you another example. This is taken from some real-world code that I did on a contracting project a while ago. So the events, we're describing the kinds of events you get in this system. You can load heat map items, so you get an array of heat map items. The camera can move to a certain latitude and longitude. You can switch heat map items, heat maps off and on. And then there's all this payment stuff. You look at that and you think, okay, so this is allowing you to see a heat map and drag the camera around and pay for it by stripe. I sort of look at that and I start to feel like I understand the business model just from that data description. And yeah, we did sell heat map data. That's what the system was. And if you wanted to teach new people what our system was about, if you wanted to onboard them, we just started by sending them to this data type. It'll tell you so much about how the system works. And again, accurately, up to date, guaranteed to be a representation of the systems, of the events that this system actually works with. Not what the CTO said it should do 6 months ago. I think a good, concise, clear description of data tells you a heck of a lot. So that's pillar one. What's the other thing? We don't just have data, we want to do stuff with it, which I would say we want to describe things and we want to describe relationships between things, how they interact. So, for this, I'm going to drag you into the rabbit hole of Haskell syntax. It's my other flame war potential in this talk. Let me teach you a little bit of Haskell syntax just because, like the data types, I think this is the clearest way I've found of talking about these ideas. So, Haskell syntax primer, all you need to know for the rest of this talk, and hopefully jumpstart your career in Haskell. Here's a Java type signature, right? We want to withdraw some money. So it takes a user ID as a string and an amount as an integer and returns a string. How do you turn this into Haskell syntax? Firstly, you remove public, that's an implementation detail. You remove the variable names, because that's an implementation detail. If you remember my previous talk, this is the one slide that overlaps, bear with me. Okay, so we've stripped it down. I should say those implementation details, they are still in Haskell. We still name variables. We're not crazy. We just don't put them in the type signature. Type signatures are the signatures of the types. The next thing you do is move the return type to the end. No idea why the return type is at the start. That's not how time works. The thing at the end is the thing at the end. And then the last, we're basically there. You just need some syntactic sugar. And that's a type signature in Haskell. And what that says is there's a function called withdrawal. It takes a string, then it takes an integer, and the thing at the end is the thing you can get back from it. Now, I look at that, and I see a fundamental relationship being described, right? There is a relationship between what withdrawn needs to do its work and what it will give you if it can do its work, right? It's just describing a simple relationship between types in and type out. So let's look at some examples of this and what we can learn from it and what it can tell you. I'm going to switch to Elm, which is almost exactly the same syntax, and the reason I'm doing that is there are a couple of error messages I want to show you later, but we might as well be talking in Haskell. They are very similar languages. So, real-world code. We had this thing we needed to do on a front-end project. We're using some like font icons, which is where you just write some very simple HTML, and you get pretty icons out. So this HTML will generate this, which is an obviously essential message to send to your users. All right. What's the implementation of that? We needed a helper function, because that was boring to write, so we wrote this helper function. The icon class, give it a name, and it just prefixes those magic class strings, right? And you get the thing out. What's the type signature of that code? It's string to string. Right? Takes a string, returns a string. If you learn one thing from this talk, it's that string to string is the worst type signature in the entire universe. I hate it, and I'm going to share this hate with you, I hope, right? Have a look at this function, foo. Foo takes a string, and it returns a string. What does foo do? What information is that communicating to me? Foo, is foo the same as icon class? Yeah, I just showed you. Icon class is string to string. Is foo too upper or too lower? Yeah, it is. Is it abbreviate, reverse? Yeah, it's that as well. How about this is foo ChatGPT? Takes a string, returns a string. That's the type signature of ChatGPT. In fact, I think string to string legitimately is Turing machine, right? Any computable function. So it's like the type signature here is basically saying, what do? I do stuff. Great, thanks. Thanks for being specific. But what's even more interesting, this isn't theoretical. This is something you can actually look at code and say it's going to be broken. So I saw that icon class function, which takes a string, which takes any string, which takes the complete works of Shakespeare and returns my phone number. I looked at that and I said, well, look, someone's going to give it the wrong input. And in fact, that happened. It got into production. Someone typed user instead of user, and we get a broken glyph icon. Nothing renders. The input is too vague. The other thing I saw in production that we had to fix was this. Someone calls icon class on the correct string, but because that returns a string, you can call icon class on the result. And we end up with this nonsense where it's double called and nested, and what's that about? Of course that doesn't work. But I think you can predict that problem just by looking at the type signature that says, oh, I'll take anything and I'll give you anything back, it'll be fine. No, that's terrible. Types should be specific. And if we make them specific, we can eliminate bugs. Let me show you. We looked at that type signature. It's horrible. Let's change it. Let's say what we mean, which is I take some kind of icon description and I return HTML. That's what it was supposed to do. That's what it did logically. We just had to teach the compiler that's what it did. So we wrote this code, right? Define a new data type, which is icon. It's got the 3 things we need. It's cheap to add to, it's cheap to remove from, so we don't put any more in than we need. We can always add more icons later. And then here's some code that takes one of those icons and spits out the HTML. And it's pretty much foolproof to use. Because it's being specific, it's very hard for it to take in something meaningless or return something meaningless. It's by pinning down the scope of the type signature, you are forced to write code that's accurate. And I think that's really powerful, and it was really powerful in practice. And I think if you look at it, it did load, good. If you look at type signatures, you can start to get clues about how the structure of the code must work, how the implementation must play out. The more specific the type signature, the more specific things you can predict about the implementation. Also, if a type signature is too general, it flags up problems. You can foresee things going wrong with something that vague, especially as you get some experience with reading these type signatures. And someone can send you something as a code review, and you can say, well, look, I will review your code, but just the type signature tells me this isn't what we mean to say. Something's going to go wrong. It also, I think, in a way, helps you structure a solution, because you look at vague type signature, you make a specific type signature, you write specific code. I think good type signatures are a way of talking to the computer and clarifying. Let me give you another example, which is similar, related, came from the same code base. Have a look at this. This is a classic decode URI thing. So a person goes to the website and the stuff after the slash. If someone goes to /account, we're going to send them to the account view. Excuse me. Account settings takes them to settings, / takes them to the front page, anything else they go to 404. Look at the type signature. I hope this gives some of you the heebs in future. Right? I think, yeah, it should make you feel uncomfortable. I could see something was going to go wrong from that. But what's interesting about this is the URI is under the user's control. They actually could start typing in the complete works of Shakespeare after the domain name. So that's correctly vague. And when I look at the input type being vague, I see a risk, but not in our code, but in the dealing with the real world. Dealing with the real world is obviously a mistake, but one we can't get away from. So I looked at that, but the output type, we can definitely be more specific about that, and we can solve problems with that. What we should do is be specific about what kinds of views we can get out, and then define a function that narrows down the infinite possibilities of string to the very finite possibilities of what kind of views we can share. So we rewrote the code very simply to look like that. What's interesting about this is where the type signatures, if they're meaningful and specific, you've taught the computer about your domain more specifically, and now the computer can actually help you out in understanding what you were trying to write. So someone wrote this code. I think it was me. Yeah, it's probably me, because it was an idiot. This code is supposed to take a view and start rendering out the HTML, right? I've summarized it a bit for the slide, of course, but this is basically the structure of it. I wrote that, and there's a problem with that, and I didn't spot it until I tried to compile it. And the compiler, which is now on my team as a teammate, says, "You've missed out not found." Couldn't do that if it was a string to string, but now it knows my domain, and this is why I switched to Elm. Aren't the error messages lovely? They're very, very nice, very clear. So the compiler is beginning to help us, and this is an axe I will happily grind all day long. I should have been more disciplined as a programmer, right? I should have known there were 4 types of view that we have to render, and I should have rendered them all, and I should have done test-driven development, and I should be disciplined, and discipline is a good thing. And I'm not saying we shouldn't be disciplined as programmers. I'm saying that our biggest weapon for discipline is to teach a machine to do it automatically, right? That's our real job as programmers, to offload work to a machine, especially when it's dumb work. Because machines are dumb, but they're very thorough, right? Far more so than humans. Dumber than humans, generally. Let's not talk about politics. But more thorough than humans, definitely. So, go back. Yeah, so we should be teaching computers things. The interesting thing is, if we start to teach computers things about our code, they can actually teach us some things we didn't know. So here's a simple example. I had this code in the same project. This is an error view. It's going to take a string, which is just going to be a title, so it should be a generically flexible input, and it's going to take an HTTP error structure, right? Some data that describes an HTTP failure, and renders out some nice HTML to the user, like a little red alert box or something. I tried a little experiment with this. I deleted the type signature and asked the compiler what it thought the type signature of this code was. Because it knows some things I don't, and it's got the patience to work out some facts in milliseconds that I would take an hour to work out, so I wouldn't work out. So if you ask the compiler what it thinks the type signature of this code should be, by commenting it out, it says, okay, it doesn't have a type signature, but I think it should be takes a string and takes an anything, a variable, any type of type you like, and returns HTML. And I looked at that, and I thought, you know what, you're right. Whilst I said this is a view that only works on HTTP errors, actually it works with any kind of problem. So I rewrote it with that type signature, and then I realized the name was wrong, and actually what I've got is a generic debugging view that will render out anything I want. And it's not like the code has fundamentally changed, but the usage has changed because my implementation was far more flexible than I've realized. Again, if you teach your computer things and you've got a good compiler, it stops being an adversary. Type systems aren't about stopping you do things. Sometimes, if you do it right, they can enable ideas you didn't have by being an assistant rather than a foe. So we've got, let's think, we've done things, and we've done relationships. That's almost the whole of programming, isn't it? Yeah, that's almost the whole of programming. We've got one more thing. These 2 ideas you can find in most programming languages. The next one is like pushing you into, hopefully, where computing's going. Another thing we need to do when we're building systems is describe context, the context in which things occur. So have a look at these functions. We've got show greeting. Takes a user, returns a string. Probably going to be like hello world, something like that. Fetch user. Takes a user ID, returns a user. If you're all experienced programmers, you're thinking user ID to user. That's probably either going to go to a database and do select star where user ID equals, or it's going to go to a REST endpoint and do /get/user/ID. You've got some intuitions just from that type signature, right? And then there's create invoice, which takes an order ID and a user ID and returns a PDF. But in what context? Well, in some languages, like the ones I'm going to try and propaganda at you later, you can start to teach the compiler about the context in which this code runs. And you can say things like that withdrawal function takes a user ID and an amount and returns your withdrawal ID in the context of being able to access a database. We can teach the compiler about context. Why is that good? Well, have a look at these pieces of code. Let's teach them about some context. Show greeting. Takes a user ID, returns a string. No context required, what I might call a pure function. It's just a simple relationship between inputs and outputs. Fetch user. My intuitions were correct, partly because I knew the slides, but I think your intuitions were correct too, right? User ID needs to access the internet in order to get you a user. That's the context in which it runs. And if HTTP isn't available, if the network isn't available, ain't gonna run. Create invoice, order ID, user ID, needs access to the database. That's the context in which it runs. By revealing context, we reveal dependencies. What kind of outer system is this going to need? Is it going to need the internet? Is it going to need Oracle? It also reveals the absence of dependencies, and I think this is equally important. Show greeting does not need a database, does not need HTTP. If the internet goes down, fetch user I can tell is going to fail. Show greeting I can tell is not going to fail. If the database is down, create invoice is the only one I know will fail. The other two I would expect to keep working. That's good. And the important thing, I've said this before, I'm going to re-emphasize it. Unlike regular documentation, I know this is true. If it compiled, I know it's correct before I even run it. I know these documents are accurate. Some of you in the audience work with documentation that's always accurate and up to date. For the rest of us, we need types. Anyone in the audience whose docs are up to date? Not a soul. Yeah, that's what we all know, right? We all know. We don't like to admit it, but we know it's true. But we can go further, because now we've got some accurate, clear descriptions of this code running in a certain environment. We can take a look at it and see if we can learn anything, because accurate documents we can learn from. So have a look at this one. Withdrawal. Look at this one. Create invoice, right? Create invoice takes an order ID and a user ID and generates a PDF in the context of being able to access a database. This, without even looking at the code, I feel like this is possibly too general. I don't think there's anything about creating an invoice in most systems that would need to update the database. I think this, again, is a little bit too vague, and I might go into my computer and create a new context which was slightly more specific. And it said, creates a PDF in the context of being able to read a database. And I think that can be quite useful, because now I want to access the database, and someone says, well, that's a security issue. Well, it may be a privacy issue, but I'm not going to be able to do delete star from user, right? I know, because my documentation has been machine checked, I know for a fact this code cannot delete star from the user table. Right? All it can do is read. That's a useful thing to be able to enhance. And then there are operational concerns, like our database is overloaded. What code do we have that we could safely move to a read-only database? I think this one, because I know it's still going to work, right? It may have latency things to worry about, but I know the code will run and execute against a read-only database. I know it. I don't think it. I don't speculate. I am sure. So this is one way in which we can use a type system to reduce the complexity of a system just by looking at the footprint and saying, nah, that's too large. I'm going to narrow it down. Another thing I think is interesting about this second type signature is I have been told my whole career that we should do decoupling. You've probably heard that mantra too. Decouple, decouple, decouple. But I have seen very few practical ways in which someone will show me opportunities for decoupling. I look at this type signature and I see an opportunity for decoupling. This seems inherently complex to me, right? Takes an order ID, takes a user ID, goes to a database and generates a PDF. I don't think there's anything inherently databasey about PDFs or PDF-ish about databases. Those are two very big concepts being complected. Any Clojure users in the room? Clojure people love the word complected. It means mixed up. All right. So I looked at that, and this is, for not being sued reasons, this is a mild change from some real-world code in the bank. Yeah, I used Haskell in the bank. Ask me about it. I looked at that and I said, well, OK, so if we create some data called an invoice, which is just the user instead of the user ID, and the order instead of the order ID, then I can pull create invoice apart into two functions. Fetch invoice, which gets an order ID and a user ID and reads from the database, and create invoice, which takes the order invoice data and turns it into a PDF. Now, I think firstly, these are decoupled, right? Database-ishness has been separated out from PDF-ishness. I think there's something really interesting about this code. Think about fetch invoice, right? Order ID, user ID, it's going to put out orders and users. You can probably guess how that's implemented, right? Select star from user where, select star from order where. Two very simple select statements. I think fetch invoice is really easy to code to write, but because it connects to a database, I think it's going to be a pain in the neck to test, right? Testing database code properly is always painful and slow, but it doesn't need that much testing, right? It's two select statements. I look at that code and think fetch invoice, pain to test, easy to write, easy to get right, probably doesn't change very often. I look at create invoice, and that's going to take some data and write out a PDF. That is going to be easy enough to test. I can just test it against reference PDFs, right? Easy to test, a pain to get right, not least because no one in the organization has thoughts about select star from user. Everyone in the organization has thoughts about how PDFs should look. Finance will worry about it, compliance will worry about it, the marketing people will worry about it, everyone will have an opinion, everyone will bike shed the invoices. But they're easy to test. So I've got two functions. By decoupling them, I've got a function that's easy to get right but hard to test, and a function that's hard to get right but easy to test. Pulling those two apart was very valuable, I think. And it all comes from looking at the type signature and saying, this has mixed two very big domains together. Maybe we should pull them apart. Yes, spot opportunities to decouple just from reading type signatures. This is good. Make things testable. And that in turn limits the scope of bugs, right? Whatever happens with create invoice, it should have the right data. Even if it looks ugly, we will get to a point where we're fairly confident that it's going to show the correct numbers. So, in my opinion, a good type system, a good modern type system, a type system that isn't just there to punch you in the face when you get the wrong size of integer, right, should be able to let you describe things clearly and succinctly. It should let you describe relationships without having to gaze into the implementation details. It should describe those clearly and succinctly. And in a beautiful world, it might even let you describe the context in which things happen clearly. So we could put the whole picture, like a very high-level summary, but very accurate high-level summary of the whole picture of what a function is trying to achieve in one line. It's very powerful. So, to wrap up, what should you do with these ideas when you go back and write JavaScript on Wednesday morning? Where do you go next? I think the first place you go next, honestly, I think the first place you go next is you start to change how you think about types, right, before you try and change the organization. So if I may give you some tips/propaganda, go and learn one of these languages. It will be some of the best brain food you ever get. This is, from left to right, this is Haskell. This is the one you choose if you want lots of books that will teach you how to do it, right? And it's full of, like, all we've learned about doing this kind of thing over the last 20, maybe 30 years. Almost all. I see you, Runa. Elm. Elm, I would still recommend. So Elm is slightly, if not defunct, then very much a resting project. Elm is a great place to start because it's kind of like the greatest hits of Haskell. The creator has called it that. It's these ideas boiled down to just the really big ideas with the friendliest compiler you'll probably ever encounter. So if you want to just get learning these ideas, it's probably a great playground. The future of the language is uncertain, I have to say that. The next one along is PureScript, which is my personal go-to language, so I have to mention it. This is, to me, it's what Haskell would be if it could throw away all the backwards compatibility stuff and just be where it got after 30 years, but from scratch. And it also compiles to JavaScript, so you can write it for the back end and the front end, which is really nice. And then we have Unison on the end. There is a man just there who will talk to you about Unison tomorrow. Unison is all these ideas in a very neat formulation, I have to say. I think it's where the usability, the UX of doing this kind of stuff is about to go, coupled with some really interesting ideas about how we collaborate on software and how we distribute software once we've collaborated with it. So go and see Runar's talk. But also, if you don't want to learn a whole language, you might want to take these ideas into TypeScript, Rust, Swift, Gleam. These are all languages that are adopting things like algebraic data types and running with them. I mean, if you learn nothing else from this talk, at least go back and be angry about string-to-string for me. I should say, so to include everybody, if there are Haskell programmers in the room and you think I already knew all this, type-driven development with Idris, I would say, introduces a fourth concept, things, relationships, context, the passage of time, I would say Idris introduces. So there's some astronaut stuff for you. And this book will literally blow your mind, fragments of mind everywhere, thinking with types. This just takes the idea of what can we express in a type signature and goes as far as I can imagine you can go. Possibly too far, definitely too far for work code you're going to put in production, but it's a good ride for the brain. But yeah, you can use these ideas at work. You can at least look at a type signature. If you're using statically typed languages, look at your type signatures and ask, are they too vague? Are they teaching me something about my domain? If you're not, maybe there's, if you're writing JavaScript, maybe there's something to be said for bringing in a bit of TypeScript, because the type system is not an enemy. It's not just there to punch you in the face when you get types wrong. It can be an assistant. It can help you to understand and communicate your domain accurately. All those things will lead us to writing better software, which I hope we do. I hope we get better at this as time goes on. Thank you very much.